about the midterm exam. There's one question in particular that I wanted to review because a number of people made some mistakes on it. But beyond that, I'm happy to take any questions that you have now that you've had a chance to look at the exam solutions and see if anything's not clear. So the one question that I wanted to go over is, maybe I should show it on the screen. Is the question in which you have to draw the geostrophic wind. And sorry, I thought this was This is question 7. You have the test, and I'm going to project it now. I hope this works. Okay. Well, the whole thing doesn't quite show up. But the question says, the diagram below shows the isobars at the surface at 30 degrees south. Gives you the air density is 1.2 kilograms per meter cubed. It says draw the direction of the geostrophic wind. And so let me just come over here. Okay, so I should turn off this light as well. Okay, so we're given a pressure field here where it's a line of 1,004 hectopascals, the higher pressure, and the lower pressure is 1,000 hectopascals. And the correct answer was to say that geostrophic wind is blowing, should be blowing parallel to the isobars. Most people got that it was blowing parallel to the isobars, and that the wind should be blowing in this direction. Now, the reason is because this is in the southern hemisphere, and it does say that at 30 degrees south in the description here. So one way to think about that is the pressure gradient force is always blowing from the high pressure to the low pressure, and so the wind would initially start out blowing across the isobars, but the effect of the Coriolis force in the southern hemisphere bends things to the left, and so the wind goes this way. It goes the opposite in the northern hemisphere, and many people drew the geostrophic wind blowing down into the left. But the result of this is that typically in both the northern and southern hemispheres, it's that swapping of the Coriolis force that gives us the prevailing westerlies in both hemispheres. So this is sort of roughly drawn in the southern hemisphere. Higher pressure is found in the tropics, lower pressure in the extratropics. So if you think of this as being north towards the tropics and south towards the South Pole, in the mid-latitudes of the southern hemisphere, you get winds blowing from the west to the east, just like you do in the northern hemisphere, because also in the northern hemisphere you have lower pressure near the poles, but the Coriolis force blows in the opposite direction. Yeah?
I was gonna say, like I knew like southern hemisphere to the left, but like I didn't realize this until probably like after the test. It's like when I always looked at it, I was like, okay, this way's right and this way's left. But like you have to like approach it from like facing from the equator down instead of like the pole up. That's how they use like the left, like the southern hemisphere.
Well, it's always to the left of what the Coriolis force is always to the left of the motion. So it's not left or right relative to the North Pole or South Pole. It's left or right relative to the motion. So if you think about this as the air starting at rest, the initial pressure gradient force would accelerate the air in this direction from high to low pressure, and then once the air starts moving, then it would feel the Coriolis force bending it to the left. Yeah?
So, just out of curiosity, I got the Coriolis right in the pressure gradient, but I think I drew it, the velocity going that way because I thought it was north. How did you do the point distribution Was it like,
I don't know, Allison might have to say that, we might have to look at that, at yours in particular. So, let's see, actually, yeah, the question didn't ask about the Coriolis and pressure gradient force. So,
so it was all 3 points going for the.
it was all 3 points going for the direction
Okay.
of the wind. Now, if we were to draw this for the northern hemisphere, the direction of the pressure gradient and Coriolis force would be exactly the same, but the wind would be blowing in the opposite way. So the forces are exactly the same in the north and south, but the direction of the wind reverses relative to the pressure gradient. Okay, then there seemed to be, most people did, try to move this a little bit. Okay. Move it a little bit further over here. Okay, now we got it. Okay. So then the second part says, calculate the geostrophic wind speed. This was a matter of recognizing the right formula for the geostrophic wind speed, and then from there, I think the only tricky part was, well, first off, you have to calculate the Coriolis parameter, but then calculating the pressure gradient. So we have a change of 4 hectopascals over 300 kilometers. And from there, it was just a matter of putting the values into the calculation. So I don't want to rush over that if there are questions about that, but I hope that's clear once you've seen the solution. And the final bit, which I know, basically we converted this final question, which said, do you think the measured wind speed is likely faster, slower, or the same as you calculated in B? I'm sorry, this just got messed up because the numbering was messed up, and we didn't find that out until later. The description at the top yeah, the description at the top said that this was at the surface. And so all that we were looking for here is that at the surface the drag force becomes important, and as a result the wind speed should be blowing slower than up here. So if I draw this again, so here's the pressure isobars. If I draw what we would expect the wind to be in the presence of the pressure gradient and friction forces and Coriolis, you would expect the wind to go like this. Pressure gradient would still be in this direction. Coriolis would be to the left of the wind at a right angle, and the friction would be opposing the wind direction. So we weren't looking for any quantitative answer here or even drawing those diagrams. I'm just emphasizing that when you add in the friction, the wind speed slows and the wind starts blowing across the isobars. So a little bit of additional context there. But instead of taking any points off for getting that wrong, we gave an extra 2 points for anybody who got it right. Yeah?
It's kind of a random question, but when friction is acting on the wind, why is the, I get that the pressure gradient force should still be perpendicular, but why is the Coriolis force not perpendicular to the isobars?
Because the Coriolis force is always perpendicular to the wind.
Okay.
Or to the motion. So, yeah, I could have drawn that here as well. The Coriolis force always perpendicular to the wind or to the motion. Yeah, any questions about that? Or now I'd open it up and say any questions about any part of the answers. Okay, well, let Allison or I know if you do have questions that come up later. Okay, so now I want to go back to talking about a more fun topic, the thermally direct circulations, and all of the things we can now explain now that we understand hydrostatic balance and the effect of temperature on the scale height. One moment. I think it's going to go now. Good, okay. So, this is the diagram that we were looking at yesterday. And a thermally direct circulation is one in which you have a region where you have relatively warm air. And in warm air, the scale height is large. And as a result, pressure decreases slowly as you go up in the atmosphere. So if the pressure is decreasing slowly, then the isobars must be spaced widely apart. We contrast that with an area over here where we have cool air. And in cool conditions, the scale height is small, which means that pressure is decreasing quickly as you go up in the atmosphere, which means that these isobars are spaced tightly together. So a small increase in height here gives you a large change in pressure. The same increase of height over here gives you a smaller increase of pressure. And we saw that what that results in is a low pressure near the surface, a low pressure over the warm surface, a relatively high pressure over the cold surface, and a breeze that develops. A sea breeze is the quintessential way that you generate these circulations. And at high altitudes, you have the reverse circulation. So relatively high pressure over the warm surface and low pressure over the cold surface, resulting in an offshore wind at high altitudes, and then a little bit of subsidence and ascent to close the circulation. And these land sea breezes blow in this direction during the day when the land is warmer, and they reverse direction at night when the land is colder. And we call this a thermally direct circulation because it's this warming of the land surface that generates the low pressure. So this is a thermally direct circulation, and the wind flows towards the warm low, ascends and diverges from an upper level high. So we saw this happens for the reasons we just said, that we have temperature controlling the scale height, and then from there we're talking about horizontal pressure differences. But this is really, all the ingredients that we need for this can be found in many other places. Anywhere that you have a temperature contrast, you can generate these sorts of land sea breezes. So sort of an obvious analog is a lake land breeze. So it's not the ocean, but you have water still. So this is found, for example, commonly in the Upper Peninsula of Michigan. Up here between, say, Lake Michigan and Lake Superior, the peninsula of land in summer is going to warm up more than these large bodies of water. And we can see this actually over just a few kilometers here well, first off, you have the warm air over the land. And so ascending air brings in the lake breeze. And one way that we see this quite clearly is just by looking at the average daily highs in the summertime in the northern peninsula of Michigan. And we see that this area that is in the middle of the peninsula, so here along this cross section, is both warmer, and there are two reasons for that. One is that the sun is warming the land more. The second is that as a result of the circulation it sets up, you have cool air flowing in from the lake. So as you go closer and closer to the lake, you have lower and lower average summer highs. So this temperature pattern is both a cause and an effect of this circulation. So clouds tend to form along the center of this. Now, we can also see this in any other place where you have a contrast of surface types. So we saw it for land, ocean, land and lake, but you can also see it between deserts and forests. If you have an area where those two are closely adjacent to each other. Because as with the land, the desert tends to warm up faster than forest. There are some places in Australia where this is an important circulation. So let's just look at this in a couple of other examples. This is one way of using remote sensing data from satellites to figure out where you have important land-sea breeze circulations. So this map up here is showing the map of where you are most likely to have clouds at 5 a.m., so at the end of night. And these dark purple colors indicate that you have a lot of clouds. And up here, the oranges and yellows indicate that you have not many clouds. So you can see that at 5 a.m. it looks like here we have a lot of clouds down here, not a lot of clouds up here. And then if we look at 5 p.m., so at the end of the day when the land has had all of its chance to heat up, the cloud cover down here looks pretty similar. But some of these places look like they're changing a lot. In particular, say here in western Mexico, we see now in the morning there weren't many clouds in that area, but now in the afternoon it's become much more cloudy. So this is an indication that in this area here on the west coast of Mexico, you've got this important land-sea breeze circulation, which is creating a lot of afternoon cloud cover in this region. If we come closer to home, the effect is not as dramatic, but if you look down here, you see relatively more clouds in the afternoon in the southeast US than you do in the morning. So again, an indication that we have these convective clouds that are being driven by this land-sea breeze. This also shows up if you look at the rainfall amounts, which is, this is the difference. This here is the difference between these two maps. So it's showing the areas where you have the greatest increase in clouds from morning to afternoon, and it's just highlighting those two regions that we were just talking about. Let's see, so another, just to put names on this, here we have the land sea breeze, and that's what we call it here. In this part of Mexico, this is really part of the North American monsoon system. Stop me at any point if you see features on these maps that look interesting or things that you're curious about, and I'm happy to talk about them. Oh, and the other thing that I labeled on here, but didn't say, is as a result of having more clouds in the afternoon, it's kind of obvious then you're going to get more rain in the afternoon as well. So this portion of Mexico, the southeast US, we're much more likely to get rain in the afternoon than we are at 5 a.m. Yeah?
Is the reason it's more dramatic in Mexico is because of kind of like the landscape that Mexico has? Like, is it more dramatic, like due to more like dramatic like temperature changes?
Yeah, if you look at this portion of Mexico, a lot of it is kind of semi-arid, kind of scrub mountainside, and that does two things. One is it's kind of, it's not a full-on desert, but it's arid. Whereas here we have a relatively green landscape. As a result, this portion of Mexico is going to warm up more because it's more arid. Furthermore, it's also mountainous around here, and that's one of my next slides, which is to say another place we see this sort of thermally direct circulation is mountain circulations. Yep, literally the next slide. So we often see that if you have a rocky, barren mountaintop and a relatively greener lowlands, you often find that mountains warm up more than does the surrounding landscape, and as a result, during daytime, you get an upslope flow around mountains due to a relatively low pressure near the mountain. and the reverse happens at night. Mountaintops tend to cool more, and so you get a downslope flow at night. So instead of calling this a land sea breeze, we call it an upslope downslope flow, but it's still the same thing. It's a thermal low generated during the day and a thermal high generated at night. This becomes really obvious when you look at some mountain areas. This is Grand Tetons National Park. Since you can see the mountains, it's obviously a daytime picture, and you see that there's this band of clouds basically following along the tops of this ridgeline because you have that upslope flow generating these cumulus clouds along here. So the same thing happens in Mexico as well. You have the combination of the land sea breeze, plus you have the effect of the upslope flow as well. They both tend to increase. Something that I didn't put on these slides, but I think is worth talking about, especially since we just talked about the geostrophic wind, you might wonder, where does the Coriolis force figure in these land sea breezes? We talked about this wind circulation, but I only talked about, the pressure differences. I never said a thing about Coriolis force. Well, if we wanted to figure out if the Coriolis force was important, how might we do that?
Coriolis parameter?
We can look at the Coriolis parameter. What else might we look at?
Is it the Rossby number?
The Rossby number, yeah. So the Rossby number expresses the importance of the centrifugal force relative to the Coriolis force. So we can do that for the land sea breeze. So the Rossby number is equal to the wind speed divided by the Coriolis parameter and the radius of the system, or some measure of its size. So this is, to remind ourselves, wind speed, size, and Coriolis parameter. And we can just put some ballpark numbers on here to figure out, is the Coriolis force going to be important or not? First off, we need to estimate what is a typical wind speed that we might experience in a land sea breeze.
10 miles per hour.
10 miles per hour, 5 meters per second. So that's a good ballpark number. So we have 5 meters per second. We have the Coriolis parameter, which is going to be 2 omega sine of the latitude. And we still need to put the size in here. Put that over here. So now we need to put in, say, what is the size that we're going to assume? So, well, any thoughts about what the size, relevant size might be?
Size of what?
Well, that's kind of the question. If we want to estimate the Rossby number, we need to put in some estimate of the wind speed that we're talking about and the size of the circulation that we are discussing. So the Rossby number, again, is useful for a sort of rough estimate of how important the Coriolis and centrifugal forces are. The important thing is not to get the exact number, but to get something that's the right order of magnitude. So I'll just pose the question back to you. The size of what? Yeah?
I saw in that last slide with the 2 lakes around Michigan, it said around 40 kilometers, so go with that.
Yeah, so the idea is we we drew this diagram where we have land and ocean. The size of the circulation is sort of, well, how far inland does the sea breeze circulation blow? And so, or, you know, that one was 2 sea breezes that were coming from 2 different lakes that were separated by some amount. Now, so we talked about it a little bit last time. Does anybody recall what is the sort of typical distance that a sea breeze blows inland? Yeah.
That was like 10 to 50 kilometers.
10 to 50 kilometers, were you going to say the same?
Yeah.
It can be more.
200.
Yeah, it can go up to 200 is sort of the maximum extent that we typically see. I will just put in 50 kilometers. 50 kilometers, or I guess I should put this in SI units, 5 times 10 to the 4 meters. And then we have to put in a value for Coriolis parameter, which is 7 times 10 to the minus 5. And the sign and latitude. Let's see, so we can put in a value here that is, for the Coriolis parameter, I mean, we could probably just keep it as 7 times 10 to the minus 5 would be fine, I think. So, just to write down the values that we're using. We have, I'm going to make it easy for myself, I'm going to say 10 to the minus 4 for the Coriolis parameter. And I'm going to say 5 times 10 to the minus 4, excuse me, 10 to the plus 4 meters. I don't know at what latitude this Coriolis parameter comes out to be 10 to the minus 4, but that's about the right magnitude for the mid-latitudes. I'm, again, doing a rough estimate here. And because I have 10 to the minus 4 and 10 to the plus 4, I have 5 up here. I end up with a value that is about 1. So what would you say? Does this make the Coriolis force important or not? Yeah, but not overall controlling. It's of the same magnitude as the centrifugal force. So I'm not saying it's right to ignore the Coriolis force, but you can see that it's not going to be the dominant player in these circulations. Now, let's think about this. If we were talking about a land sea breeze that went 200 kilometers inland, then this wouldn't be 5 times 10 to the 4. This would be 2 times 10 to the 5. If this were going 200 kilometers in, this would drop to 0.25. And then we'd say, well, the bigger the sea breeze circulation, it looks like the more important the Coriolis force is. And that's what you expect anyway. You know, if the wind is blowing in some direction and you have a small Coriolis acceleration to the side, you're only going to see that if you're blowing a long distance and accumulating that acceleration over a large distance. Okay, so we have mountain valley winds that we showed here. We'll look at some other examples here. So we're just going to larger and larger scales here. If we look at monsoon circulations, also thermally direct. So the classic case of a monsoon circulation is South Asia, where you have a continent that warms up. Asia, particularly India and Southeast Asia, warm up during summer, more so than the ocean. As a result, you have a flow inland, which reverses in the wintertime as the land cools more. So again, you have a low pressure, a thermal low, which which is driving the wind inland. And during that warm season, summer season, is also, as a result, when you get the most precipitation. So this is showing a distribution of the precipitation by month of year. So you can see that most of the precipitation falls during the summer months, June, July, and August. If you go to December and January, this region of India gets really very, very little precipitation during the dry winter monsoon. So thermally direct circulation really has an immense influence on the climate of South Asia. South Asia, oh, sorry, we're going to show a little bit further complication here. So in a non-rotating system, we would have, in which we neglect the Coriolis force, we would have sort of simple convergence at the low levels towards the thermal low. At the upper levels of the atmosphere, we would have a high pressure system and diverging air flowing away from it. This is what we would get if we neglected the Coriolis force, but as we just showed, the bigger the system that we're talking about, the more important the Coriolis force becomes. And certainly for something as large as the monsoon system, we have to account for the Coriolis force. And so instead of having this sort of direct convergence into the thermal low, we have a much more complicated circulation around the Indian monsoon. So this left panel here shows what the monsoon might look like on a non-rotating Earth, and this is more realistic. So at the low levels, we have convergence over India and South Asia, some cross-equatorial flow that, because of the reversing Coriolis force, reverses direction as the air crosses the equator. And then if we go to high altitudes, we have a high pressure system, and again, some other complicated motions around the monsoon high in the upper atmosphere, upper troposphere. And I started to say that South Asia is not the only place where we find monsoon circulations. They're quite widespread. So the Asian monsoon extends over a very large region here. We talked about the North American monsoon, which it primarily affects Mexico, but also extends a little bit further up into the southwest US. The Sahel region of Africa also has a monsoon system, and these shown in blue are the ones in which you have precipitation during summertime. So you have thermal heating of the land in summertime, in northern hemisphere summertime, so June, July, and August. So these blue regions are the areas where you get peak precipitation during June, July, and August. If we go to the southern hemisphere, things reverse, or the seasons reverse, and so you have peak heating of the land in December, January, February, and so then you get the peak monsoon seasons in the southern hemisphere land regions as well. Yeah.
I was just kind of curious. So like I would say like southeast and Florida gets more rain than where the North American monsoon is, but because its monsoon is defined like an amount of like 5 months, and so it looks like the dry areas tend to have monsoons. But if you're in a wet area, like it's impossible to have a monsoon, it seems.
Yeah, so
It's kind of weird.
we do get more of our rain during the summer here than we do in winter. But the contrast in precipitation between our summer rain and our winter rain is not strong enough that it would typically be called a monsoon system, at least according to this. The people who created this map said they were defining the monsoon as regions that have 70% of their annual rainfall in 5 months. Yeah, so the same types of patterns happen here in the southeast. We get heating of the land in the southeast US, and particularly in summertime, and we get more rain in summertime, and it's driven by the same thermally direct circulation, but for other reasons, we still get rain in the wintertime, and so it's not really considered a monsoon circulation. Yeah?
What's up with that part of Canada? Like, how do they get so much rainfall?
You could say that about Canada in general, right? No, I'm kidding. I don't know what's going on there.
It's the same thing as Russia.
Oh, I do. I'm sorry. This is along the Rocky Mountains here, and in some parts of those regions, you do have an increase of precipitation due to mountain valley circulations, which can be bigger in summer. So although I haven't looked at the detail, I think that that's probably what's going on there. You can see that it's a small region, so I wouldn't say that there's a monsoon circulation in that tiny little patch, but yeah. Other questions? Okay. So we can go even further and say that on the biggest scales, we see thermally direct circulations controlling the weather patterns of the tropics as a whole. So along the equator, we have greater heating due to the sun throughout the entire tropical belt. The heating is greater here than it is in the subtropics because the sun is more directly overhead in the tropics. As a result, we get warm thermal lows all along the equator and relatively cooler conditions here, which causes the Hadley circulation. So a low pressure near the surface, ascending air diverging to the subtropics of both hemispheres, and a compensating circulation downward. So this is a thermally direct circulation on a planetary scale. But it's the same overall driving factors that we've been talking about with the land sea breeze. We can see this if we look at pressure maps. So typically what we find is if you look at a pressure map, you typically find the lowest or lower pressures in the tropics. So there tend to be thermal lows. So this is the July sea level pressure. You tend to have thermal lows that are kind of along this band here, displaced a little bit north of the equator because of heating due to the land. Generally lower pressures here. If we look in the upper troposphere, we see that sort of co-located with those lows at the surface, we have higher pressure in the middle troposphere. So that's a clear indication that we're seeing a thermally direct circulation with low pressure near the surface, high pressure directly on top of it in the middle and upper troposphere. Another place where we see thermally direct circulations that have an important impact on weather is the El Nino-La Nina system in the Pacific Ocean. So typically what we have in the Pacific Ocean is that the Western Pacific, let me orient you here first. This is the coast of South America here. This is Indonesia over here. So along the equator, we tend to have warmer water and warmer air over Indonesia, the Western Pacific, and relatively colder water and colder air in the Eastern Pacific. As a result, we have a circulation in which there tends to be more convection and more precipitation over Indonesia, and relatively drier air over the Eastern Pacific. However, during the El Nino conditions, that warm water from the Western Pacific sloshes over towards the Eastern Pacific. And so you bring this relatively warm mass of water over here, and this moves the low pressure from over Indonesia towards South America, and the convection and circulation follows it. So here we have a case where, again, it's warm air generating a surface low, rising air, precipitation. And so we see that thermally direct circulations, again, are playing a huge role in controlling the precipitation of this region of the world. We can also see thermally direct circulations on the scale of individual storms, and the biggest, baddest thermally direct storms are hurricanes, in which you have a circulation here that looks kind of like what we drew for the pressure cross section of the land sea breeze. So here we have a warm region where the isobars are widely spaced, and this warm air is sitting in an environment in which the isobars outside are relatively more narrowly spaced. So as a result, we generate warm, low pressure air in the middle, relatively high pressure air at the surface here. And so we have convergence into the middle, ascent, and divergence at the top. As a result, you can see here the slope of these isobars is an indication of how strong the pressure gradients are. And so in a warm system like this, we have very strongly sloped pressure surfaces near the surface. And the slope of these isobars decreases as we go up in the atmosphere. As a result, another feature of these warm core cyclones is that we have the highest winds near the surface, because these pressure surfaces have their greatest slopes near the surface, and then weakening winds as we go up with altitude. And that's reflected in the wind speeds then. We have, of course, extremely strong winds near the core of a tropical cyclone, and the winds at the top are much weaker. So it's really looking like, gee, we can understand, it seems like most all of these weather systems in terms of thermally direct circulations. Can we understand all weather systems in this way? And the answer is definitely no. There are a lot of circulations which are not thermally direct, but sort of one of the most obvious ones is what you typically think of as a mid-latitude cyclone. So not a tropical cyclone, but an extratropical cyclone. And these systems are not driven by a warm core surrounded by a relatively colder environment. They are driven by warm air towards the equator and cold air towards the poles, and it's that temperature contrast that's driving the strength of these. Another way of looking at this is in terms of the temperatures that we find in the middle. We tend to find that cyclones in their center tend to be colder than their surrounding air near the surface, and that actually reverses as you go towards the tropopause, or the upper troposphere. So cyclones, extratropical cyclones, tend to be cold near the surface and warm at high latitudes, or excuse me, at high altitudes. The reasons for that are complicated, and we're not going to talk about those. I just wanted you to be aware that thermally direct circulations explain a tremendous amount of weather on local scales for land sea breeze, up to global scales for the Hadley circulation and monsoons and El Nino, but they don't explain everything. Yeah?
So, the slope at the surface seems like it's not as much. Is that indicating like a lesser wind with this?
Yeah. So that's an interesting contrast between these cold core cyclones and warm core tropical cyclones. So if it's cold here, then you have narrowly spaced isobars here and relatively widely spaced isobars outside. As a result, the slope of the isobars increases as you go up. We contrast that with, so if we look at this one, we have strong slopes near the surface, and as you go up, they weaken, weaken, weaken. And we really have the opposite in cold core cyclones. We have relatively weak gradients here. Because this is cold core, the slopes of those isobars increase as you go up in altitude. So what would you, where would you guess you'd have the strongest winds?
The top of the storm?
Yeah. So extratropical cyclones can be just as intense as a hurricane. It's just those winds are way up high and not damaging structures at the surface. But yeah, cold core cyclones or extratropical cyclones have their maximum intensity in the middle and upper troposphere, unlike hurricanes. Well, that's where I wanted to wrap up for today. So I'm happy to keep talking about this stuff. It's kind of exciting, but feel free to head out, and I'll stick around to talk with anybody who wants to stay.
I do have a question. Didn't you say earlier in the semester how like some hurricanes, when they go up in latitude, they can kind of like transform into like
Yeah.
a mid-latitude
Uh-huh.
cyclone? So does that warm core that they have just turn into like a cold core as they keep going up? Like, do you know what I'm
Yeah,
asking?
they have
Okay.
to make that transition, which
Okay.
is why not every storm does it, but
Yeah.
some do. Yeah. Yeah, that's right. So these storms are sometimes called nor'easters when they follow a path that comes up the eastern U.S. But they're, you know, it's just that this is a storm track, and so people have given them a special name if they're following this typical track. The storms really aren't that different from other cyclones that propagate in different directions.
Go ahead.
Yeah.
Go ahead.
I was gonna ask you, can you go back to the El Nino slide?
Yeah.
I was a little confused.
So like, you said like,
So,
the diagram.
where's the low?
Yeah.
So the low is following where the warm water is. So the warm water is here. So the surface low is here. Here we have, oh, I see, it was labeled up here and it's not down here. Yeah, so up here it's labeled as the low, here is the high, here it kind of reverses here. So in both cases, the low is where the warm water is, the ascent, convection, and the high is where the cooler water is and the sinking air.
Okay.
Yeah.
So in the notes from yesterday, you, like I don't know if you wrote this down or if I wrote it down like wrong, but it says thermally direct is when wind blows towards warm low pressure.
Mm-hmm.
But like on the slide with the Hadley circulation, wouldn't
Yep.
that be going from warm to cold?
So here you have warming that is mainly in the tropics. So you're generating the warmest temperatures right here on the equator, relatively cooler temperatures to the north and south. So you have a warm low pressure here.
Okay, that's what I was
So the air is flowing into that warm low pressure, ascending through convection and diverging. So there's an upper level high over the tropics as well.
So thermally direct is when it's always converging
Yeah.
where it's warm.
Yes.
Okay.
So thermally direct means that the low is created by the warm air. In contrast, in this type of system, we have a low pressure here, but it's driven by other forces.
So when I saw the difference actually started falling, it was like, I just would have like, small